Hello and welcome back. Some videos ago we talked about energy conservation, and this is the idea that energy cannot be created or destroyed, that it is always a conserved quantity. And so however much you have before a process of this energy, you'll have after the process as well. The energy forms that we'll be dealing with this semester are kinetic energy, potential energy, and heat energy. And remember that when we lump kinetic energy and potential energy together, in other words, we sum them together, then we define that as mechanical energy. Mechanical energy isn't a different type of energy, it just simply is the sum of the potential and kinetic energies. The two different types of potential energy that we're going to be dealing with this semester are associated with the two fields we'll be dealing with this semester, which are the gravitational field and the elastic field. Gravitational field gets the symbol G. The elastic field is getting the symbol S. Why is that? Because we are going to mainly be dealing with springs, and springs will get the symbol S, just to remind us that this is a spring. Other elastic entities also can have potential energy, but again, we're really going to just be focusing in on springs here. K is known as the spring constant, and in this video, we're really going to be looking mainly here at the potential energy associated with springs and how we use that to look at other quantities associated with the spring's motion. So here's a spring, and again, this is the elastic entity that we're going to be focusing in on this semester. And so let's just draw what this is going to look like. So we're going to have some spring, right? And let's say we have a mass connected to the end of the spring, and the spring has a spring constant K. So K is equal to the spring constant. And this is a quantity that is measured empirically in a lab, and we'll talk about that more in just a moment. The force exerted by a spring, and I'm going to give that also the subscript S, force associated with the spring, is equal to minus Kx, where X is equal, I don't want to say equal, is position of spring's endpoint with respect to its equilibrium position. Okay, so now let's notice the units for K. So what are the units for K going to look like? Remember, when I put brackets around a quantity, I'm just talking about the quantity's units. For the units for the spring constant are going to be the units for force divided by the units for distance. So this is going to be a Newton per meter. Okay, so why the negative sign? Well, let's imagine this being our equilibrium length. So we're going to reference that as x equals 0. In other words, when I place the mass at the end of the spring at this location and I let go, nothing happens. The spring is not compressed and it's not stretched. The end of the spring is at its equilibrium length. So that's what I call x equals 0. Now let's imagine that we grab this mass and we expand it away from its equilibrium position. So now we've stretched the spring out some distance. This was our x equals 0. We've stretched it out some distance x from its equilibrium length. So now what happens? Well, we've got a force being exerted on this mass by the spring because we have stretched the spring. And the force exerted by the spring on the mass is in the opposite direction to the displacement of the spring from its equilibrium position. So I would measure x as positive when I move to the right. That would be my normal choice of a coordinate system. In other words, in this direction, I'd say x is greater than 0, and in this direction, I would say x is less than 0, just using our standard coordinate system. And so that would mean I would measure x as some positive value as I pull the mass away from its equilibrium position to the right. So I would be plugging in a positive value for x. However, we know the force exerted by the spring is to the left. The spring wants to restore itself to its equilibrium length. And so this negative sign comes from the fact that the force is always oppositely directed to the displacement of the end of the spring. Notice this also holds true if I compress the spring. So let's say instead I had compressed the spring so that now here's my mass and here is my equilibrium x equals 0 position, but now I've compressed this mass a distance x from its equilibrium length. Now I would be measuring x as negative because I have compressed it or moved the equilibrium length to the left. So x would be a negative value that I would be plugging into this equation. This negative and the negative value for x would cancel, leaving a positive, telling me that the force exerted by the spring should be positive. And indeed, we know that's true. The spring is going to try and push back to its equilibrium length, and it's going to push the mass to the right. So the force exerted by the spring and the direction of the displacement of the end of the spring are always oppositely directed, and that's why the negative sign comes there. Now, how do we measure K in a lab? Well, we ask our lab tech to take the spring in there, and so what he'll do is he'll take his spring and he'll place the spring on a table, and he'll place the mass, a mass on the end of the spring, and he'll pull on the mass so that he displaces the spring. Let's say this was the equilibrium length of the spring, x equals 0. He will displace it some known distance x from its equilibrium length. He has a force meter that he has attached to the mass, so he knows how much force is necessary to hold this mass, stretching the spring a distance x from its equilibrium position. So if he knows the magnitude of the force he has to exert to the right to hold the spring from compressing back or from pulling back to its equilibrium position, then he knows the force being exerted by the spring because there's no motion this way. So the force he's exerting with his force detector is the same as the force exerted by the spring, and those two forces having the same magnitude, he's able to read out the force exerted by the spring on his force detector, and knowing x, he can calculate K. So that is how K is calculated. It's very easily done in a laboratory environment, and then reported for a specific spring. And of course, as springs age, their spring constant could change. So measuring a spring constant just before an experiment is important in the integrity of the experiment as well. All right, so the potential energy associated with the spring, remember, is 1/2 kx squared. So notice it doesn't matter whether I expand the spring a distance x or compress the spring a distance x. If these distances are the same, then the potential energy that is stored in the spring's field in the expanded scenario is exactly the same as the potential energy stored in the spring's field in the compressed scenario. Again, assuming that these expansions and compressions are exactly the same distances, then the potential energies associated with those two are exactly the same as well. So now we stretch this spring away from its equilibrium position and we let go, and what happens? Well, this mass starts to move back toward the equilibrium position, and what happens to x? as we are moving toward the equilibrium position, x is getting smaller and smaller and smaller. And when the mass reaches x equals 0, it doesn't come to a screeching halt. Now it starts pushing the spring, compressing it. So now when we are fully compressed, then the mass now is located distance x from the equilibrium length of the spring. So now we're fully compressed, and this is assuming there's no friction on the surface to eat away the energy and convert it to heat energy on the surface. So we're assuming completely frictionless surface. But notice that this fully compressed spring, now the mass instantaneously stops, and it doesn't just stay there. Now again, the spring is trying to push the mass back toward the equilibrium position, and so we get the mass moving back toward the equilibrium length. It doesn't come to a screeching halt there. Now expands the spring. When the mass stops, we're back in this scenario, and that mass just oscillates back and forth and back and forth. And notice that at the endpoints, when the mass is instantaneously at rest at these two endpoints, all of the mechanical energy is in the form of potential energy, and the masses are furthest away from the equilibrium length of the spring. And right when the mass is at x equals 0, moving through the equilibrium position as it is going from expanded to compressed, when it moves through that equilibrium position, all of the mechanical energy is in the form of kinetic energy, and that's energy of motion for the mass. So in this scenario, fully expanded, all ME is PE. It's all in the form of potential energy. Fully compressed, same scenario. All mechanical energy is potential energy. And at x equals 0, all mechanical energy is kinetic energy. What about in between? What about as the mass is moving from fully expanded to the equilibrium position? Well, then the mechanical energy is in both forms. Some of it's in potential and some of it's in kinetic. But when we have only the spring's force doing work, as is true here, and notice that it is not the only force acting. We have a normal force being exerted by the surface on the mass. We have a gravitational force being exerted on the mass by the Earth's gravitational field. But those two forces are at right angles to the displacement of the object. So they don't do any work. So the work done by the normal force is 0, and the work done by gravity is 0, because the displacement of the mass as it's oscillating back and forth is always at 90 degrees to both of those forces. Of course, it's not at 90 degrees with respect to the force exerted by the spring itself, but the spring is a conservative force. Therefore, it works to conserve the system's mechanical energy, and since it's the only force doing work, then the mechanical energy will indeed be conserved, and the sum of potential and kinetic energy at one point is the same as the sum of potential and kinetic energies at any other point. So when we're fully expanded, all the potential energy, all the mechanical energy is in the form of potential energy. When we are fully compressed, all of the mechanical energy is in the form of potential energy. When the object moves from the maximum expansion to the equilibrium position, then the energy is in both forms, mechanical and potential. When it reaches the equilibrium position, there's no potential energy, right? X is 0 at that point, no potential energy. All the energy is in kinetic energy. Of course, it's moving the fastest there. Then it starts to compress, right? And as it moves from the equilibrium position to fully compressed, again, the energy is in both forms in that realm. And then when it's fully compressed, back to potential energy. So the energy is sloshing back and forth between potential and kinetic as this system oscillates back and forth. And again, remember, this was all hinging on the fact that we're dealing with completely frictionless surface, ideal conditions. So gives you kind of an insight to how we apply potential energy associated with the spring. And recall from the previous video that we realized that since the net work is always written as the change in kinetic energy, when we're dealing with the conservative force, which is also applying to a spring, then we can write that as minus the potential energy. So applying it specifically to the spring, we could write that as minus, and open up parentheses, the change in potential energy 1/2 kx final squared minus 1/2 kx initial squared. So that would give us an idea of how to calculate the work done by the spring as a mass moves from one position to another connected to a spring. So we'll look at some problems next time, applying these to word problems. See you next time.